Woo. Next one up, 6.1, differential equations and slope fields. All right. So it says here, let's talk about this one being differential equations. I'll just read it to you. As an equation involving a derivative is called a differential equation. That's what you need to worry about, this part right here. The part where it says the order of a differential equation is the order of the highest derivative involved in the equation. This definition part here, you don't need to worry about until probably next year. All right. For now, because we're only going to deal with first order differential equations because they all have the first derivative. So let's take a look at what an example looks like. So here I have the derivative, and it tells me here my derivative, dy dx, is equal to 3x squared plus cosine x. And you got to remember that just represents the slope of my equation at any point. And you got to remember when we were doing antiderivatives, right? Our antiderivatives gave us that plus c. Okay? Well, that means it gives me a possibility of finding all my answers. Okay? And so I want to be able to find all my answers for the equation. Well, that's what kind of differential equations gives us. And so differential equations, the same thing as a derivative. But how do I handle them differently? Okay? So remember when I said dy over dx does not mean divide unless it's handy. Again, here's another case of where it's handy. And so what I would do is quote unquote multiply both sides by dx. And when I do, I end up with dy is equal to 3x squared plus a cosine x dx. Well, how can I get rid of the dx part? Well, the way I can do that is by taking the antiderivative of both sides. And remember, when there's nothing over here, so the antiderivative of 1 dy is y. And then I take the antiderivative of this. What function gives me the derivative of 3x squared? Okay, well, it's going to be 3x cubed over 3. Plus, what derivative gives me cosine? Oh, negative sine, or sine. Plus, don't forget the c. Great. I go ahead and I simplify, and I go, well, y is equal to x cubed plus a sine x plus a c. Always a c. And this represents every single function that this derivative. Why? Because of this plus c. I have infinitely many solutions, all based off of I need to know more to find out an exact solution. But these are all of the solutions. So the question is, well, how can I find just one? Great, glad you asked. Well, that question is answered in my next example. In this example, okay, here the difference is they give me a point at the end. So this point, what I'm going to do is I'm going to go ahead and plug in. I'll plug in by set up the same way. dy over dx is equal to e to the 2x minus 3x. And then I go ahead, separate on both sides. And when I do this, I get dy over is equal to e to the 2x minus 3x dx. How do I get rid of the dx's part? I integrate both sides. 1, so y is equal to. Okay, technically this one right here, the antiderivative of e to the 2x, I need to use a u substitution. I'm going to go through that really quickly, okay, and be able to tell you that this is going to be equal to e to the 2x, 1/2 e to the 2x minus 3 to the x squared over 2 plus a c. Now again, if you didn't pick this up right here, go back and check out u substitution and work it that way. All right. For this purposes, I'm just going to be working through those kind of quickly so that we can see the important stuff, what's different and what's new. So now what's different about this one is they give us that point. So what can I possibly do with that point? You're right. plug it in. So now when I plug in, the y value is 1/2 is equal to 1/2 e to the 2 times 1 minus 3 1 squared over 2 plus a c. I simplify, and then I'm going to add the 3/2 over. When I add the 3/2 over, I get 2 is equal to 1/2 e squared plus a c. I can then subtract the 1/2 e squared, and I get 2 minus a 1/2 e squared is equal to c. All right, and you might think, woohoo, I found everything, I'm done. Not quite yet. You need to put everything together because they're asking for the particular solution. So my particular solution is y is equal to 1/2 e to the 2x minus 3x squared over 2 plus 2 minus 1/2 e squared. There is your complete answer. Okie dokie. Okay, same as before, we're just adding one more step. Cool. Let's see what happens now. We're going to get to, that's the differential equations. So now we're going to talk about slope fields. Okay, slope fields is something that we can create through a differential equation. Because it gives the differential equation, since it's the derivative, gives us the slope at any point x, y. That information can be used to draw a small piece of the linearization. Remember what linearization is? That's when I have my slope. If I'm trying to find different slope of different stuff, linearization is when I look in really close. I see everything kind of has a line to it, right? Every little slope has a line. This is what linearization is. Every little point has its own little slope. Does that make sense? Okay. So here we go. It can be used to a piece of the linearization at that point, which approximates the solution curve that passes through that point. Ooh. Repeating that process many times yields an approximation called a slope field. So here we go. Let's take a look at what a slope field looks like. Boom. This is what a slope field looks like. Okay. What? What is this craziness? Okay. So if my differential equation was dy dx is equal to some function in terms of x and y, okay, actually this particular one I'm going to cheat because I can kind of see what this is and I know a little bit more. This particular one is just a f of x, okay, it's a function of x, okay, and so I look at that, and anytime x changes, so does my slope. And it gets me all these little points. So what does that mean? Well, what this means is that any time that my x value changes, my slope changes, and my little itty-bitty slope changes. So when I mean itty-bitty, I mean this itty-bitty slope. And it doesn't matter what y is because it's only a function of x. So I move over here to 1, comma 1. That represented the slope there. And I can move any point, it doesn't matter again what y is, that slope is always the same. Always, always, always the same. Now notice when I move over a couple, and I move over a little bit on x, my slope changed a little bit. But that slope stays the same all the way up. Great. And that's true all the way across for x. So what does that mean for these lines? These lines represent possible solutions. As you can see, the solutions look very similar to each other, all depending on where I start. These points here can be my starting point or my initial point. And the way I like to look at slope fields is when I have my initial point that starts right here, this is where the wind takes me. All of a sudden the wind pushes me back down, kind of look like reading a wind chart, pushing me around. And this right here pushing me around or down. But what if my balloon didn't start over there? What happens if my balloon started here? Then the wind would take me this way. Round and through and down. But what if my balloon didn't even start there? What if instead it started here and I wanted to go, it would push me this way. But then I could also use the same slope field to find out, well, where could it have gone prior to? Where could it have come from? And that's what makes the slope field so amazingly cool, is that I can find out where given just a dot, a point, I can figure out where my function's going and where it should have been. So let's take a look and see if we can draw one. So here I've got this weird slope field graph going again. Let's say my first point starts here at 1, 0, 1. What's going to happen to my graph? So I'm kind of, again, being pushed by the wind down, 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 down. Oh, it's pushing me flat. And then now it's pushing me up, 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 up. But what if I didn't start there? What if instead I started here? This is my start point. Again, the winds would sit down here and push me down, down, and come push me back up, 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 up. But that can also tell me where I should have gone. Kind of interesting, right? I think so. So how do I create one of these slope fields? Excellent. I'm glad you asked. How do I create one of these things? Okay, well, what I'm going to do is I'm going to create a chart. It's going to be dy, dx, x, y. Okay? Because in theory, these things should all rely on that. And I notice that this is x is cosine of x, so here I'm going to choose something here. I'm going to choose pi over 2. Okay, I'm going to choose, let's not choose it there. Let's choose it here. This will be pi over 2. This one here will be pi over 4. And then this one over here, I can be 3 pi over 4. Okay, so when I go ahead and I choose this, well, dy dx, so I can go ahead and say, what I do is I choose points. So if I start here and say, well, 0, 0, and then pi over, and then 0, okay, pi over 4, 0, and what if I choose the next one being like pi over 2 over 0, and then the next one 3 pi over 4, 0. Okay, but those would just give me these points. So my linearization of these points, so 0, 0. So when I plug in 0, 0 in here for x and y, well, there's only an x coordinate, right? So when I plug in 0, cosine of 0 is 1. Cosine of pi over 4, square root of 2 over 2. Cosine of pi over 2, 0. Cosine of 3 pi over 4, okay, is negative square root of 2 over 2. Okay, so then how does that get represented here? So it's saying at 0, 0, my slope is 1. So I make a slope of 1. Approximation, okay? Square root of 2 over 2, okay? That's going to be a little bit less than 1, so I can make it a little bit flatter. At pi at 0, so I make a flat line there. 3 pi over 4, negative square root of 2 over 2. Okay? And if you notice, that's just those 4 points. Well, what else do I have to do? Well, I have to do the rest of them. But maybe you should see a pattern here that it doesn't matter what I put in for y, right? It doesn't matter what I put in for y. X is the only thing that's controlling it. And I already found all of this, so if I wanted to find out what is happening here at, at 0 pi over 4, wherever this is at, if I'm going to keep the same thing, it doesn't matter. It's always going to be 1. 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 This one's just a little bit flatter. Always the same. A little bit flatter. A little bit flatter. A little bit flatter. A little bit flatter. This one's always 0. Always 0. Okay? This one's going to be negative. Didn't matter, so now I keep going. This would be 0, 0, 0, right? And then I have to think, well, what happens if I go to negative pi over 4? Okay, well, what happens when I go to negative pi over 4? Okay, That's the same thing as saying 7 pi over 4. So again, that's going to be, positive square root of 2 over 2. What happens if I go to negative pi over 2? It's still going to be me 0. Okay? So I can go ahead and then I could stretch this out a little bit more. Okay? These are all going to be 0, 0, 0, 0, 0. These are going to give me positive pi's over 2. Is that right? Okay. Yeah. Positive pi's over 2. A little bit flatter than that. Okay. So then it goes, well, what graph? There's my slope field. I'm done. Okay. But what graph does this get to? What graph does this get to? I follow the winds and say, here's my starting point right here. Here's my starting point right here. If I follow the winds, follow the winds. Huh. Looks a little bit like, oh, I don't know, sine. Huh. That's interesting. So, boom. Let's go what's next. Okay. dy dx is now going to be equal to negative y. So again, which ones does y control? And again, we'll just have here this be 1, 1, 2, 2. So what's controlling my slope field? The only thing controlling my slope field are my y's. So it doesn't matter what my x's are, my y's control what my slope field is going to be. So if I just go ahead and I plug in negative 2 for y, negative 1 for y, 0, 1, and 2, tells me my slope is a positive 2, positive 1, it's opposite, it's 0, negative 1, negative 2. So again, what does this look like? So the question becomes, alright, so again, y's are in control. So when I'm at a positive 1, my slope is a negative 1. So it's a negative 1, negative 1, negative 1. And when it's at a positive 2, it's at a negative 2. Now, you don't have to be precise, as long as it looks steeper. So steeper, steeper, okay? Steeper. Oops. That one kind of failed. Steeper. Okay. And what happens at here at 0, 0, 0, 0, 0, 0? At 1, negative 1, it's positive 1. So again, no matter what happens with x, y is the one controlling this. Positive 2. And all of a sudden it's like, whoa, what just happened here? Wow, I created this field, but what is it going to give me as far as a graph? So again, if I start up here, what's happening? The winds are blowing me down, but then all of a sudden it makes me stay straight. Same thing here. The winds are blowing me up. If I were to start over here, the winds are blowing me up, but then it makes me stay straight. It looks like a horizontal asymptote. Kind of cool. All right, let's try another one. So this one, what I want you to do is I want you to fill this out, make a choice as far as what is changing, or what's controlling the slope field. Is it dy dx? I mean, is it x or is it y? All right, I'm going to pause the video. You guys can go ahead and do this. And here's your graph. Okay, I couldn't get to the rest of these here, so there you go. And this is what you should be getting for your slope field. Again, x is the one that's in control, so no matter what x is, it's always going to be the same vertically and horizontally. I mean, excuse me, vertically from wherever x is at. So whenever I try to graph something, what is this actually going to look like? Huh. And so I grab this and I go, well, what's it going to look like? Here's my ball. Comes in, being blown, 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 there. And again, when I'm looking at this, the slope of 1/2 and the slope of -1 and positive 1/2 and -1 and positive 1, they're just relative to each other. I just have to see that this doesn't have to be exactly 1, but this better be flatter than this one. Okay? Does that make sense? That's all you're looking for when you draw a slope field. So let's take a look at some examples. So here's some stuff that where X and Y aren't always the ones that are controlled. So, solely in control. So I take a look at this one here. I got to start thinking to myself, what's happening here? Well, in 2X, X is the only thing that's in control. So no matter what X is, it's always going to be the same. So what that means is that if I start here and I look up and down, these better all be the same because X is the one that's in control. And when I look at that, the only one that does that is this one right here. This one goes here. All these other ones, when I go up and down, they're changing. So now I got to figure out what's the difference between X, Y, and X plus Y. Well, I have to think to myself, the easiest way to describe these or try to figure these out, because all these are relative. I have no idea what's happening. But I don't know, like, if this is 1/2 and that's 1, I don't know. But what I know for a fact is I know where zeros are at, right? So I know where zeros are at. So, because they're flat lines. Like this one over here has a whole bunch of flat lines here. This one here has got flat lines going here, up and down. So when is X plus Y equal to 0? And that's what I have to think to myself, well, if they're opposite, like if one is positive and one is negative, X is positive 1, Y is negative 1, I'm going to get 0. And it doesn't matter where that's going to happen, as long as one's positive, one's negative. Now I have to think again, where does that happen? Well, it happens in quadrant 2 and quadrant 4. All of a sudden I have this line of zeros, because when X is 2, Y is negative 2. And over here, when X is negative 2, Y is positive 2, it's going to get a 0 for a slope. Oh, so that's why this one goes over here. And this one, when it's 0, well, one of either if X is 0 or Y is 0, I'm going to have a 0 slope. And so it's kind of hard to see here, but that's where your 0 slopes are overtaking. And it's kind of hard to see on the graph here because they're not in different colors. Okay? And that one goes here. All right. Now that you've had a little bit of practice with this, I want you to do the next one. And I'm going to go ahead and pause the video. I want you to think about it. Okay? And when we're done, I will tell you which one matches where. Actually, we'll do this first. We'll call this one A, B, C, and D, and I'll tell you where they match. Bang. There's your answers. All right. Now, I'm going to tell you that the two top ones were kind of tough for me to just. What made them tough was the fact that, okay, well, let's do the easy ones. Square root of Y. So if Y is negative, I'm not going to have any slopes at all. So that's why it's A. There's nothing there. Okay? When here's this differential equation here. Again, they're all being dealt with in terms of X, so everything up and down should look the same. Everything up and down on B is the same. On top of that, when X is equal to negative 2, I do not have a slope, and it's a vertical straight line. So that's why that one's B. Now C and D, what I was initially looking for is hey, they're both going to be somewhat the same. The only difference is the X and the 2X. I was looking to try and find out when Y is equal to 2 that I would have that negative, a straight up and down slope. And I kind of get it here. But it's not precise. And I didn't like that as much. I didn't like that it, so it's like not quite at positive 2. So here's what I'm going to say is what made the decision. I knew that C or D had to be matched up. I knew that D, okay, that this one over here, this D right here, this one here had 2X and this one had X. So I compared the same spots. I looked here and I looked here and I said, which one of those two slopes looks steeper? And I chose D because it's 2X on top instead of just X. Okay? I know, a little tricky. You can blame me later. Let's see what's next. Your homework. There it is. All right. So I know this one was long, but it's the second to last one that you have to worry about. We only got one more after this. Good luck.